Welcome to the fourth lecture of Electrical Engineering 525. This lecture takes us into Chapter 3, and the first problem here comes from Section 3.1. In this problem, which is problem 3.1-2, we're told the following. It says that the current density on an actual short dipole antenna can be written in this form. Notice that that is a z-directed current, and it is a function of z. And what we're asked to do in this problem is to find an expression for the associated charge density. Now, as you might recall from previous courses, the relationship between the current density J and the charge density rho is given by this equation right here, that the divergence of J is equal to minus partial rho partial t, where t is time. Now, when we convert that equation to the phasor domain, again, this is the equation in the time domain. When we convert it to an equation in the phasor domain, that partial t simply becomes j omega, and so we have that the divergence of J is equal to minus j omega rho. And we'll work with that equation, that form of the equation. So if we divide each side of if we flip the sides of this equation and then divide each side of the equation by minus j omega, we get rho is equal to minus 1 over j omega times the divergence of J. And of course, 1 over j is the same thing as minus j, so we can bring a minus j into the top, and minus of minus j is positive j. So this is j over omega times the divergence of J. Now remember that the divergence, the formula for the divergence of a vector is partial jx partial x plus partial jy partial y plus partial jz partial z. This is the formula for the divergence of J in Cartesian coordinates. So rho is equal to j over omega times that quantity. And we remember, as was noted above, J here has only a z component, and so the partial jx partial x drops away, partial jy partial y drops away, and we're left simply with partial jz partial z. And if you look at jz up here, which is everything to the right of j hat, you see that it does not vary with respect to x or y. It depends only on z through this absolute value term, and therefore, returning down to this equation, the partial derivative with respect to z is really just an ordinary derivative, because jz varies only with respect to z. It does not vary with respect to x and y. So we have rho is equal to j over omega times the ordinary derivative of jz with respect to z. And when we plug in for jz into that formula, we get this, j over omega ddz of j naught sine of beta times delta z over 2 minus the absolute value of z. Now, the only thing that is the least bit challenging about this problem is this absolute value. How do we take the derivative of a term involving the absolute value? And there's several ways that you could approach this problem, and I think that the way that I'm going to show you is probably the simplest, but it is also maybe the most tedious. So let's just see how this will go. Okay, we have j over omega times d dz, and we simply note that this term here in the brackets will be equal to j naught sine of beta delta z over 2 minus beta times positive z if z is greater than 0. Because, after all, when z is greater than 0, the absolute value of z is simply equal to z itself. So we get beta times delta z over 2. That comes down here. And then if we substitute z for the absolute value of z, we'll get beta z here. And that is, this expression here is good whenever z is greater than 0. Now, on the other hand, when z is less than 0, the absolute value of z is the same thing as negative z. So in that case, we would get beta delta z over 2, and then minus beta times negative z, and minus beta times negative z is the same thing. Here's the minus beta times negative z, and so this comes down, and we will get this expression here. So we have j over omega ddz, and j naught sine of beta delta z over 2 minus beta z if z is greater than 0, and times the sine of beta delta z over 2 plus beta z if z is less than 0. And now we are ready to go ahead and take the derivative, and j naught is just a constant, so when we take the derivative of this first term, the j naught just comes outside of the derivative, and the derivative of sine of u is equal to cosine of u times du dz. We're thinking of this term here in the parentheses as u, and if we think of that as u, then du dz is minus beta in this case, and down here, if we think of this as u, then du dz will be plus beta. And so that's what we get down here. We bring down the j over omega, and the j naught just comes right down because it is a constant. And then here's our, again, this is sine of u, so the derivative is cosine u, and then du dz will be minus beta in this case, and plus beta in the second case. And so this is what we get after we take the derivative. And to be honest, we could just go ahead and stop right there if you want to. This is a correct final answer, but it's not in a very convenient form. We could write this more compactly, and so the rest of this problem will consist of doing a few manipulations to write this more compactly. And you know, this is not a course on mathematical manipulation, but it's sort of nice to be aware of some of these little tricks, and so that's why we'll take this opportunity to look at it. Now, what we are hoping to do is to combine all of this here into one expression. And so a way that we might do it is the following. Okay, we'll bring down the j over omega, and then in this first term, we'll bring down the minus beta, we'll bring down the j naught, and then we're going to also introduce a term z divided by absolute value of z. Now, since z is greater than 0, the absolute value of z is always equal to z, and of course z divided by z is 1. So this is just another way of writing 1. And you might think, well, what is the purpose of doing that? That's just making the expression more complicated rather than less complicated. But we'll see the point in that in a moment. Everything else we just bring down. The cosine of beta delta z over 2 minus beta z we bring down right here. Now, for the second expression, we bring down the beta, and we bring down the j naught, but then we're going to pull a trick here. We're going to put a negative sign here in front and have z over absolute value of z for this term as well. Now notice, since we're in the region z is less than 0 for this expression, z is a negative number, so z divided by absolute value of z is negative 1 in this case. So this is negative 1, but we want it to be equal to what we have up here, which is positive 1. And so we have to multiply this by this negative sign out here so that overall this will be positive. And immediately then you can see why we have done this, because by pulling this trick of introducing this term z over the absolute value of z, we have been able now to make these two terms, which look different up here. Now down here you see that at least outside the cosine argument, outside in this leading coefficient, now the coefficients look exactly the same. Now we'd like to make what's inside here look exactly the same as well, and then we could combine these two expressions. Well, let's see how that will go. It's similar to what we've just done. So we now bring down the minus beta z over absolute value of z j naught. We bring that down. That's the same for both terms. And we bring that down here. And of course we bring down the j over omega. And then we note, in going from here down to here, we note that when z is greater than 0, z is the same thing as the absolute value of z. So we'll just write this z that's right here, we'll write it as absolute value of z. But when z is less than 0, then z is equal to minus the absolute value of z. So we're going to replace this z here by minus absolute value of z down here. And you can immediately see why you want to do that, because now we've accomplished our goal of making the argument of the cosine function look exactly the same for these two cases. So now everything that is outside of the cosine function looks the same, and everything that is inside of the cosine function looks the same. And so now we can write this more conveniently, more compactly, as just one expression. So rho is equal to minus j over omega times beta times j naught times z divided by absolute value of z times, oh wait, we don't need this j naught again. We've already written j naught there, so we don't need to write that down twice. Okay, so so there we go. So again, rho is minus j over omega times beta j naught z divided by absolute value of z, and then the cosine, and we've factored out the beta here, so cosine of beta times delta z over 2 minus absolute value of z. And that is good for all values of z where we have this short dipole antenna, but now at the terminals we don't, where z is equal to 0, we don't try to use this formula. And of course you can see why here. Z divided by absolute value of z is not defined when z is equal to 0, but that's really not a problem for us, because the antenna exists for z greater than 0 and for z less than 0. It doesn't really, the antenna does not exist at z equals 0 itself. That's where the terminal for the antenna is. So we do not need to be concerned about the fact that this equation does not make sense at z equals 0. So here is the expression, the final expression for the relationship for the charge density for this problem. And now let's go to the next problem. This is problem 3.2-4 from section 2 of chapter 3. And in this one, we're asked to show that the ohmic resistance of a half-wave dipole using equation 2.173 or 2-173 is given by this formula here. R naught, that's the ohmic resistance, is equal to Rs, the surface resistance, divided by 2 pi a. A here is the radius of the antenna, times lambda over 4, where lambda is the wavelength at which the antenna is being operated. Well, we're told to use equation 2-173, and 2-173 tells us that this ohmic resistance is equal to this expression right here, where this I sub A is the current at the input terminals of the antenna. So if we use the formula here, we have this formula 3-1 gives us this current I of Z on the half-wave dipole antenna, and is equal to Im sine of beta times lambda over 4 minus absolute value of Z. And this is good for absolute value of Z less than or equal to lambda over 4. So if we use that to substitute into the expression for R0, we'll get the following, okay? So R0 is equal to, first let's handle this term, 1 over IA squared. Now IA is the current at the input terminals. Well, at the input terminals, Z is equal to 0, so we need to evaluate this current at Z equals 0, and we'll get Im times the sine of beta times lambda over 4 minus absolute value of 0, which of course is 0. So we just get Im sine of beta lambda over 4. And keep in mind that we need to take the magnitude squared of that, and so that will give us this expression here in the denominator. Then the next term is Rs times 2 pi over A, which we have brought down here. And then we have the integral from minus L over 2 to L over 2 of magnitude of I of Z squared dz. Well, again, I of Z is right here. So when we square that, we get Im squared sine squared of beta times lambda over 4 minus absolute value of Z dz. So now let's go about evaluating this. Okay. Beta here in the denominator is 2 pi over lambda. So that's one substitution we can make right away. When we square everything here in the brackets, we get Im squared and sine squared. The Rs over 2 pi A will just bring down. Im squared is a constant, so it comes out of the integral. And then an easy way to do this integral is the following. Note that the integrand here is symmetric about Z equals 0. What I mean by that is that when we plug in any positive value of Z, let's say Z equals L over 4, that would fall in this range between minus L over 2 and L over 2. So plug in Z equals L over 4. And then think of what we get if we plug in Z equals minus L over 4. Well, in both cases, we take the absolute value, so we'll be left with L over 4. So in other words, this integrand has the same value for Z as it does for negative Z. That's why we call it a symmetric function. It's symmetric about Z equals 0. And because of that, we can simply integrate this function over half of that domain. This is a symmetric domain, and this is important. You have to have not only a function that's an even, but this is called an even function. So it is even about Z equals 0, or symmetric about Z equals 0, whichever you wish to say. But we also, for this trick to work, it has to be symmetric limits. And the limits are indeed symmetric. So what we can do is change the lower limit to 0 and then put a factor of 2 out here. So the integral of this even function over these symmetric limits is equal to twice the value of that function from 0 to L over 2. And notice that we've done one other thing here. Since we now have this function over the range from 0 to L over 2 instead of the range from minus L over 2 to L over 2, we're only considering positive values of z here. And that being the case, we can make the further simplification that over that range, absolute value of z is simply equal to z itself. So that's why we can write down z here rather than absolute value of z. And in fact, that's another benefit of pulling this trick, is that it's an easy way to get rid of the absolute value. Now, it doesn't always work. If you don't have symmetric limits, you could not do that. But when you have symmetric limits, you can frequently pull some trick like this. Okay? So now let's see how to simplify this. Well, in this expression here in the denominator, the lambdas will cancel, and 2 pi over 4 is the same as pi over 2, and the sine of pi over 2 is 1, and 1 squared is 1. So we're just left here, and notice also im squared here will cancel with im squared here. So we're just left with rs over 2 pi a times 2. Those 2's cancel, so we have just rs over pi a. That's all we have on the outside. And then here we'll have integral 0 to L over 2. Now, an identity that you might remember from trigonometry is that the sine squared of x is 1 minus cosine 2x over 2. If you don't remember that very well, it's easy to derive, because we have cosine of 2x is equal to cosine squared x minus sine squared x. That just comes from the cosine of a sum formula, because cosine of 2x is the same thing as cosine of x plus x, and so you get cosine x minus sine x, or cosine squared x minus sine squared x. But remember that cosine squared x is the same thing as 1 minus sine squared x. And then we pull down the other sine squared x. And so we get cosine of 2x is 1 minus 2 sine squared x. And therefore sine squared x is 1 minus cosine 2x over 2. Similarly, cosine squared x is 1 plus cosine 2x over 2. So those are useful identities to know when you're doing integrals of this type. So resuming then, so we're going to make the substitution that sine squared of this is 1 minus cosine of 2 times that divided by 2. Okay, going to the next line, we'll bring down the rs over pi a, and we're going to break this integral up into 2 parts. We have a 1/2 here, so we'll integrate for 1/2, and then minus, and then we have a 1/2 again, and we'll get this term. And in the argument of the cosine function, I've gone ahead and multiplied out the 2 beta times lambda over 4 and 2 beta times negative z. Now proceeding, we bring down the rs divided by pi a, and when we integrate 1/2 from 0 to L over 2, we just get L over 2 times 1/2, or L over 4, and then minus 1/2 here, integral 0 to L over 2. Remember that beta is 2 pi over lambda, so we'll substitute that in here and also here. And when we, in this one, 2 times 2 pi over lambda, of course, will be 4 pi over lambda times z. Now, coming down, L, the length of the half-wave dipole is half a wavelength, so that's lambda over 2, and lambda over 2 divided by 4 will give you lambda over 8. And then we bring down this, and bring down all this. Now, notice that 2 times 2 pi over lambda, well, the lambdas, notice the lambdas here will cancel, And then we have 2 times 2 pi is 4 pi divided by 4. So we just have pi and then minus 4 pi z over lambda dz. Bring down the rs over pi a. And here is lambda over 8 minus 1/2. And now we're going to go ahead and take the cosine of a difference formula. We have cosine pi, cosine 4 pi z over lambda, plus sine pi, sine of 4 pi z over lambda, dz. Coming down to the next line, we bring down the lambda over 8, bring down rs over pi a, bring down the 1/2, and now cosine of pi is -1, so this is negative, and then we have cosine of 4 pi z over lambda, and of course the sine of pi is 0, so all of this drops out. So we're just left with this term right here, and that can be written then as rs over pi a. We're bringing the lambda over 8 here, and then we have a minus sign in here, which can be combined with this minus sign to get plus 1/2 integral 0 to L over 2 of cosine of 4 pi z over lambda dz. That's a easy integral. It has almost the form of cosine u du, but to get it in exactly the right form, we need a 4 pi over lambda on the inside, and when we multiply on the inside by 4 pi over lambda, we need to multiply on the outside by lambda over 4 pi. So this is where the lambda over 4 pi comes here. Everything else we just bring down, so we get lambda over 4 pi, and then of course the integral of cosine u du is sine u, so we have sine of 4 pi z over lambda, evaluated from z equals 0 to z equals L over 2 is the upper limit, but remember L is lambda over 2, so that becomes lambda over 4. And now we're almost done. We come down one more time, rs over pi a, bring down lambda over 8, and then the 1/2 times lambda over 4 pi will be lambda over 8 pi. And at the upper limit, when we stick in lambda over 4 for z, we'll get sine of pi. And at the lower limit, when we stick in z equals 0, we get sine of 0. And of course, both of those, sine of pi is 0, sine of 0 is 0, so this whole term drops out, and we have rs over pi a times lambda over 8, or rs lambda over 8 pi a. And that is indeed the quantity that we were expected to derive. So that's how that derivation would go. And one of the main features of that is simply to get a little more practice with handling these absolute values, especially inside integrals. And now the final problem that we'll do for this lecture is just really sort of a plug and chug problem, but it's still worthwhile to see some of the ideas involved in this problem. So this is also from section 3.2, and it's problem 3.2-5. And it says, use this result that we've just derived, this one about the ohmic resistance. This is the relationship now here. Remember, this is the ohmic resistance. Rs is the surface resistance. And lambda is equal to the wavelength. And A is the radius of the antenna. So it says, use that result to calculate the radiation efficiency of a half-wave dipole at 100 megahertz if it is made of aluminum wire 6.35 millimeters, which is 1/4 of an inch in diameter. And it says, assume the radiation resistance is 70 ohms. Now, we're going to be doing some calculations here, and you'll notice that I will carry along the units as we proceed with this calculation. I believe that is an important thing to do, because if you'll carry along the units, it will help you to detect any errors that you might make. Because after all, if you end up with some equation where if you're calculating something, like in this case, we're calculating efficiency, which should be dimensionless. So if we end up with an efficiency of 1 kilometer, we know that something is wrong. So I strongly suggest that when you make calculations like this involving units having these dimensions, that you carry along the dimensions with you. So, anyway, the equation for the efficiency is that it's for the radiation efficiency is that it's the radiation resistance divided by the radiation resistance plus the ohmic resistance. And of course, we've just derived this formula for the ohmic resistance, which is Rs lambda over 8 pi a. So let's work with that. Now first, let's consider this Rs. Rs is the surface resistance, and from chapter 2, equation 171, we have that the surface resistance is equal to the square root of omega mu over 2 sigma. So this is where we're going to do most of the work involved in handling these quantities with dimensions. So let's see how this goes. Now, certainly you're not expected to memorize this, but if you look on page 783, for aluminum, the conductivity sigma is equal to 3.5 times 10 to the 7th Siemens per meter. And a Siemens is the same thing as an inverse ohm. So this is 3.5 times 10 to the 7th inverse ohms, inverse meters. Omega is equal to 2 pi f, and they told us that the frequency is 100 megahertz. So we have 2 pi times 100 times 10 to the 6th hertz, and a hertz is an inverse second. And then finally, mu, this is given on page 784, is equal to 4 pi times 10 to the minus 7th henries per meter. Now, I'll be honest with you, I forgot myself what a henry was, how it was related to other MKS units. And so whenever I forget like that, I'll go try to find some equation that involves that term. And one that I know and that is in the material we've been talking about here is this is one of Maxwell's equations. The curl of E is minus partial B partial T, which is, of course, B is mu H, and so it's minus mu partial H partial T. Now, if I use this equation that the curl of E is equal to minus mu partial H partial T, I can figure out what mu is in terms of MKS units as follows, okay? We know that E is volts per meter. And then when we take the curl of that, well, that's going to involve taking derivatives with respect to space. So we'll get another 1 over meters there. So this ends up being simply volts over meter squared. Now I'm going to bring down mu. That's what I'm interested in, is figuring out the units for mu. And then H is an ampere per meter. And then we have a time derivative here, so that gives us a 1 over second. So we have volts over meter squared is equal to mu times amperes over meter second. And so if we multiply both sides by meter second and divide both sides by ampere, we get mu is equal to volt meter second over ampere meter squared. Now we can cancel a meter in the top and the bottom. That's volt second over ampere meter. And a volt per ampere is an ohm, so this is the same thing as an ohm second divided by a meter. Those are MKS units. That is the equivalent of a henry per meter. So in other words, we see here a henry is an ohm second. So we have 4 pi times 10 to the minus 7th ohm seconds per meters. And we will see that if we carry this along, that all these units are going to work out just right. So now that we have omega, we have mu, we have 2 sigma, we can go ahead and substitute into this expression for Rs. And by the way, here I've left out a factor of 2, so we have 2, because remember this is again, here's 2 sigma, so we have 2 times 3.5 times 10 to the 7th, and inverse ohms, inverse meters. Now let's okay, the 2 times 3.5 will give us 7.0, and here we have 7.0. Okay, but the important thing I want you to notice, because these kinds of manipulations, this is just turning the crank. What's more important right now is looking at what happens to the units. So let's look at this. Okay, here in the numerator we have seconds, we have inverse seconds, and then seconds. So that cancels, and we're just left with ohms per meter right there. And then in the denominator, we have ohms to the -1, meters to the -1. So we can bring both of those upstairs since both of them are to the -1 power. So we end up having ohms per meter, that's from right here, and then ohm meter when we bring both of these upstairs. And everything else, okay, here's the 2 pi times 4 pi gives us 8 pi squared. 10 to the 8th times 10 to the -7 gives us 10. And then 2 times 3.5 times 10 to the 7th is 7 times 10 to the 7th down here. Now notice that the meter, this meter here will cancel with this meter, and we have ohms squared. But remember, we are taking the square root of that, so the square root of ohms squared will just be ohms. So we can pull ohms outside of the radical, and then everything else inside the radical is just a number, and that's perfect. That's exactly what we expect, because remember, RS is the surface resistance, and so we do indeed expect it to be in terms of ohms, and that has worked out just right. So that gives us confidence. That doesn't prove that we're coming up with the right answer, but it certainly gives us confidence in what we're doing. And so when we do that, and let me see, I'm going to have to make an adjustment in this value right here, because remember I had forgotten that factor of 2. Now that we have the factor of 2, it will have to be adjusted. So I'll take a break for a moment and calculate a new value of RS. Okay, the value for RS, after we make that correction, the value for RS is equal to 0.0034 ohms. And now we're ready to finish this problem. Remember, from above here, ER is given by this expression here. And so we'll bring that down now. ER, this is repeating that formula. ER is equal to the radiation resistance divided by the radiation resistance plus RS times lambda over 8 pi A. And we're told to use the radiation resistance equal to 70 ohms. So we have 70 ohms divided by 70 ohms plus 0.0034 ohms. That's the surface resistance times lambda over 8 pi A. Now, recall, we need to find lambda here. And recall that F lambda is equal to the speed c, the speed of light in this case. So lambda is c over F. C is 3 times 10 to the 8th meters per second, and F is 100 megahertz, or 100 times 10 to the 6th inverse seconds. Multiply top and bottom by seconds to get rid of this, and we'll have meters per second times seconds, so just meters. And 3 times 10 to the 8th, 100 times 10 to the 6th is the same as 1 times 10 to the 8th, so we have 3 meters. And notice that the units, the dimensions here turn out to be exactly right, because wavelength should of course be a length, and of course 3 meters is a length. So that looks good. And now we're finally ready to finish this problem. We'll have here 70 ohms in the numerator. In the denominator we have 70 ohms, and then 0.0034 ohms. And lambda, we just argued, is 3 meters and 8 pi, and then of course the radius of the antenna A is 6.35 times 10 to the -3 meters. So the meters here cancels with the meters here, and therefore the units on, or the dimensions on this term will be ohms. The dimensions on this term will be ohms, and of course when we add ohms to ohms we get ohms. So we have ohms in the bottom. That is ohms in the denominator, ohms in the numerator. They will cancel, and we will get a dimensionless quantity, which is exactly what we expect for the efficiency. And doing the math, we get this for a final value of efficiency of 99.91%. And so again, some of the highlights of this problem. One is the importance of carrying along the dimensions and calculations. Another interesting feature is to notice how the surface resistance depends on the frequency, and as the frequency goes up, the surface resistance of the antenna will go up. And finally, we do note the high radiation efficiency we get for the half-wave dipole antenna. So that concludes lecture 4, and good luck.